Hello again, I'm John Anderson, and this is Enhanced Content for Engineering and Technology courses, Module 10, the last module. We are at the end of the road. So, in Module 9, we talked about the components of the composites kit from aircraft spruce, and now we want to take those components and use them to actually make a part. We're going to talk about structures of labs and other issues there. At the end of this, we will again have student activities, and the student activities will actually encompass making some parts. So, hope you enjoy this module. Let's get started.
So in this module, we're going to talk about using the actual kit from aircraft spruce. In the last module, we went through and opened the kit up, and we looked at the individual composite components, I guess is the right way to say that. And in the student activities, I asked you to go pull the material safety data sheets, the MSDSs, for several of the major components that you'd be working with, and look at what personal protective equipment was required and the first aid procedures if something were to go wrong. As I'm sure you've seen from the MSDS sheets, these are fairly innocuous materials. There are some issues there. You can have some reaction on your skin to the resins and to the fibers. Some people are very sensitive to fiberglass fibers, and they tend to get the pieces of glass embedded in their skins and the pores of their skin, and causes some irritation. I would suggest that you wash with cold water and try to clean up as much as possible, and to minimize the amount of skin that comes in contact with the materials. I'm fairly sensitive to fiberglass, and as long as I take precautions, it's not a huge issue. It's not a life-threatening issue anyway. You just end up with a little rash. So, safe handling of composite components. That was our first objective. To set up a lab in a way that all of the materials, all of the precautions were fairly well documented and were available to the instructor and the student. The second is to demonstrate some techniques of wet layup of fiberglass composites. You've looked at several films on wet layups, and the student activities for this module have some more films in it on wet layup. There is some technique involved, and there's some artistry in doing wet layup of composites. We can talk about that forever, but until you actually go in and get your hands dirty, so to speak, you're not going to get a really good feel for that. So I would urge you at the conclusion of this module, during the student activities, that you actually go through and make some fiberglass layups before you have your students do that, so that you can get a feel for how that works. The next objective is to demonstrate the effect of fiber orientation in laminate stack design and final part properties. Typically, that's not exactly true. I don't know if it's typical or not, but in many cases, composite labs have the students making some part that is aesthetically pleasing or performs some function, as opposed to looking at the effect of the manufacturing process on final part properties, on things like mechanical strength. So we wanted to take an opportunity to not only demonstrate the art of wet layup and all of the steps that are necessary in order to make parts, but also we wanted to have some measure of how you design parts, what the effect of fiber orientation, which is one of your primary design elements in composites, and on the quality of your work, that what effect that has on final part properties and those. So we needed something to measure there, and mechanical properties. We decided to talk a little bit more about that in a minute. And the last thing is, in designing this lab, we wanted to use easily obtained components packaged as a complete kit to minimize storage and physical lab requirements. That is, we wanted you to be able to open the box on the kit, run your labs, and then dispose of everything else, so that you don't really have to have a set physical lab that's for composites. And we also wanted to do this in a way that you could reproduce results from year to year or class to class. So we wanted to use the same chemistry in the kit, and Aircraft Spruce has provided us with a neat way of doing that. So let's talk about impact of fiber orientation on mechanical properties. We've talked about this before in the introduction to composites modules, and we said that the tensile load in a composite structure is carried primarily by the fibers. The fibers along the length of the fibers, the strength of the fibers is many, many, many times greater than that of the resin, even after it's cured out. So the resin is there to provide shape and to hold the fibers in position, but the tensile load is actually carried by the fibers. The maximum strength of the part is going to be in the direction of these fibers. So it makes sense that if we have requirements of our part for strength in certain directions, we want to orient the fibers to accommodate that. So tensile strength is probably the most obvious indicator here. And in a perfect world, we would probably have designed a lab to make tensile specimens so that students, once they were finished, could pull those tensile specimens and do a stress-strain curve and compare one specimen to another depending on the orientation of the fibers in the plies in our part, in our specimen. The problem with tensile specimens is that you've got to have a tensile tester. And even the most rudimentary tensile testers are fairly expensive and require some expertise to operate and some effort to maintain them. So the picture that you see here in the upper right-hand corner is of a tensile tester at Oregon Tech. This is the load frame for the tensile tester, and this the position of the load frames is picked up by sensors and fed into a computer program, and that plots out, plus the output of a strain gauge, and that plots out the stress-strain curve. So you're looking at load applied, force applied, versus stretch or strain, deformation, if you will, of the specimen. And you can see here, this is a specimen that's been stressed to failure. You see it's starting to break fibers up here in these portions. So that would be a great way for us to relate fiber orientation or ply placement to mechanical properties. But it's expensive. So we wanted something that was less expensive so that we could do on a casual basis. And stiffness is also impacted. So we thought about this and we decided that although stiffness is probably not as obvious an indicator as tensile strength, it is an important factor in designing parts, and it's easier to measure. So we came up with some ways of doing that. These range from semi-sophisticated to Rube Goldberg. This is my first attempt at setting up to do deflection on composite specimens. And you can see the equipment is, I took a piece of metal here, sheet metal, and I clamped it with the specimen to a folding table using a set of welding clamps. And I took a water bottle and filled it with water to a predetermined weight, measured that on a set of scales, and then tied that off on the end of the tensile specimen. So I have this piece of sheet metal as a reference, and then my composite specimen deflects, and I can take a ruler or a gauge and measure how much it's deflected by looking at the gap here. So that's a real simple way of doing it. We've also done this in a couple of different ways. This is one that was done by one of our partners. They clamped the composite specimen to a table, used a set of duckbill vice grips to clamp onto the end so they could reproduce the actual clamping area on the end of the specimen, and they could spread that out over the width of the specimen. And then they tied a weight, a known weight, onto the end of these vice grip, duckbill vice grip clamps. And then they measured the deflection at the clamp. So you have a known location every time on the clamp to reproduce how you're going to measure this. Probably the best system we came up with was to have a series of weights or blocks that hold a specimen down and apply a large surface area to the specimen on a table. Notch the specimen at the end so that you have the load always applied at a known distance from the end of the specimen. Apply the weight and use a reference here that's also held down by the same weights and look at the deflection that way. So these are fairly inexpensive, easy things to do using common materials laying around. And I'm sure if you put your imagination to work, you can come up with something at least as good as what we've done. The first step in making these specimens is to actually cut the fiber. So you can see here, this is a student at Oregon Tech. We've laid out the fiberglass cloth, and you want to use both the unidirectional and the bidirectional cloth, and we've laid out the ply orientations. So the ply orientations are based on a clock system, if you will. That is, we assign the zero direction parallel to the selvage edge of the fabric, and then we can orient our cuts, our fiber orientation at 45, 90 degrees to this zero direction or negative 45. And so we can mark on our fabric where we want to cut the plies, the parts to go in the laminate, and then we can cut those out. So you see a student here using a Sharpie to mark the patterns on the cloth, and obviously you want to try to do this in a way that maximizes the cloth available. So you might consider taking a piece of paper cut to the dimensions of the cuts, the plies that you're going to have, several pieces of paper, and laying those out on the fabric and moving them around until you get the most efficient pattern for cutting the laminate out. Once you get the plies cut, then you need to mix the resin and hardener. You do not want to mix the resin and hardener until you're ready to use it. So there was a video, I think we looked at it last time, last module, that talked about how you use these pumps. These pumps are set up for ratios, to give you a ratio. So you have a kit of 3 pumps in your kit, and a package of 3 pumps, I should say. The largest one goes in the resin, and it's for the 105. And the smallest one gives you a ratio of 5-to-1 on volume. So for every pump here, you get 5 times the volume of a pump here. So we put the resin into a mixing cup, and then we put the hardener in. We want to use the same number of strokes on our pump for the resin and the hardener so that we maintain our 5-to-1. You want to prime these into a disposable jar or cup or something so that you know that you have a full stroke and the pump is completely full of liquid. Once you've dispensed the appropriate amount of resin and hardener into a mixing cup, you want to use the stir sticks that are provided in the kit. Stir this up. Make sure it's stirred very well. You want to do this by hand fairly slowly. You want to try to minimize introducing air bubbles into the liquid. In the student activities for this module, I suggest an exercise where you put a small amount of resin and hardener into a small mixing cup and take your tongue depressor, or your mixing stick here, actually is a tongue depressor, and once you get it mixed, stick the tongue depressor into the liquid, hold it above the surface of the liquid, and observe that it runs off of the tongue depressor and back into the mixing cup. Then wait a minute, put the tongue depressor back in the liquid, hold it above the surface, and observe the liquid running out again, running off the tongue depressor again. Do this at 1 minute intervals for about 10-15 minutes, and you'll observe that the liquid flows slower and slower. That is, it's getting thicker, or the viscosity is rising. That means that the resin is actually cross-linking, and so it's starting to harden, or it's starting to cure. This will give you a feel, doing this exercise will give you a feel for what the pot life or open time of this resin is. So we said before, you need to get the resin onto the fabric while it's still in a low viscosity state, because you want to wet out the fibers as well as possible. And if the resin is in a liquid state, then it can flow around the fibers and form a good physical, mechanical bond there. So you've got your laminate laid out in a stack that has to do with your fiber orientation. And I think we call out for 4 layers of cloth in the laboratory. You want to lay these out on a piece of plastic or a piece of board that you've waxed, or you have some sort of mold release on the bottom so that you don't stick to the table, of course. And then you use 2 tools to make sure that you work the resin into the fiberglass cloth, into the stack of fiberglass cloth. One of these, you see the student on the right, is using a spreader. You have 2 spreaders included in your kit. These are flat pieces of plastic. I think they're probably high-density polyethylene, so the resin doesn't stick to them very badly. So we take and we pour some of the resin out of the mixing cup into the center of the cloth, and then use the spreader to work it out over the cloth. That won't get the resin all the way into the nooks and crannies of your fabric. You're going to have to use a brush for that. So you wet out a brush and you take and push the liquid into the fabric. It's easier to see than it is to to describe, but as you work the brush across the fabric, you'll see that the liquid on the top that sits on the top of the surface of the fabric is being worked into the fabric. So you want to be sure that you get liquid, the resin, worked all the way through this stack of fabric layers. And then you have to allow this to cure. So I would suggest that this is a 1 or maybe 3-part lab. First is the introduction to the laboratory and to the components and to the safety procedures and so on. Second would be actually, and perhaps in the first, you cut the ply layers and kit up each part. And then the second lab would be mixing the resin and applying it. And then you need to wait at least 24 hours. And you demold or take the laminate, the part, off of whatever you laid these up on. And if you're going to do bending specimens, you're going to need to cut across here and get your specimens. I would suggest that you make a large part using a piece of cloth so that you have enough material here to cut it and make 4 specimens. And then as opposed to trying to make the specimens too wet, you're going to get a more consistent specimen. Your stiffness of your specimen is going to be partially dependent on the size and shape of the width of the specimen. So the more uniform you can get that and make those parts, the better off you're going to be. So that's the stiffness specimens. There are other things you could use this kit for. One of the common composite slabs that I've seen out there is using either fiberglass or carbon fibers to make clipboards. And the interesting thing about the clipboards is that you can actually go through and customize those. You could put letters in, emboss letters in, such as the OIT here that you see, or you could put a graphic in, a picture. In this case, we made up some with our project logo. And what you do is you just insert this graphic under one layer of the laminate material. So it appears to be embedded in the material. You can purchase these clips for the clipboard and use a hand pop riveter to rivet them to the fiberglass. And I will include, as part of the student activities, I'll include a document that shows you where to get those pop rivets and the clips.
Well, that concludes Module 10 and concludes this course. This is the last module in the course, as we said before. I hope that you've enjoyed or at least gotten something out of the course. It's been a lot of fun working on this. So good luck and see you next time.